Abby, how are you doing?
Yeah, hello everyone. Hopefully you can hear me all right. Let me just share my screen. Thanks very much for inviting me to present today. It's a great opportunity and great to follow on from Yari as well. So thank you for that, Yari. Hi everybody. For those of you that don't know me, I work at Loughborough School of Design and Creative Arts with some fabulous people. So I work alongside Richard Bibb. We used to have a chap called James Gardner and Joe White, particularly within this particular research area, specialising in 3D printed wrist splints. So I'm going to be talking about some of our prior research based on this. Started off with some PhD work, but subsequently got funded by Versus Arthritis, previously Arthritis Research UK. Apologies if it's a little bit slow, my laptop is ridiculously old. So just an overview as to what I'm going to be talking about today. I'll talk about traditional splinting practices, primarily based from observations are made through NHS clinics and such like, and through textbooks and interviews with therapists. So over the years, I wanted to highlight some of the hurdles to adopting digital interventions as well, although I'm pretty sure a lot of it has already been covered. But I'll just summarise some of the key points, but specifically within the context of wrist splints. And then I'll talk a little bit about some of the prototypes that we've developed subsequently since the start of all of this, where our interests lie. So just as an introduction, so on the images shown, these are wrist immobilisation splints. So these are typically made for patients with long-term degenerative conditions like rheumatoid arthritis. The intention being to stabilise, promote movement in certain areas, say around obviously flexion of the fingers and the thumb and such like. And these are custom made for the individual. So these are relatively simple, but therapists spend an awful lot of time making truly custom fitting devices to suit the individual patient and their needs, based around making sure that their lives are better and enabling them to go about their everyday lives. But there's various negative aspects to this, so they can be quite time consuming to make, particularly for novice hand therapists who are starting off with their training. They're not all that aesthetically pleasing. They can get sweaty, uncomfortable, Velcro sticks to stuff, and yeah, basically it's quite a laborious process in making these. So the overall typical process that you might find is that the therapist asks the patients to put their hand palm down on a piece of paper or a piece of thermoplastic. They then draw a rough template around there with typical landmarks of particular interest, and this will vary depending on different types of splints. Once they do that, they transfer that onto a low temperature thermoplastic. They put that into a hot water bath, various different types of thermoplastics with different properties. And then it then becomes soft and pliable, and then they can cut it to shape with scissors and various other things, and then they can directly form it onto the patient. Depending on the thermoplastic that they're using, it might take a few iterations of this. So waiting for the thermoplastic to heat up and then forming it and all these other bits and pieces takes time and repetition. They can also make localized adjustments with, say, heater guns and various other bits and pieces, but the overall process is really very it relies a lot on the tacit knowledge of the therapist and their relationship with the patient, understanding what the patient needs, and customizing it to suit. And just with these seemingly basic splints, there's lots of discrete design features in here that a lot of other research groups may have overlooked, for example. So just a few of them. Often therapists flare the proximal edge so it doesn't pinch and rub on the forearm. That's pretty critical. Often the edge is rolled around the thenar boundary to help ease that sort of interaction between the skin. Contoured edges to enable flexion at the metacarpal phalangeal joints, so actually enabling you to move your fingers is pretty critical with these particular splints. You want to enable people to go about picking things up, having a cup of tea, that sort of thing. And similarly, having things like rolled distal edges as well. In addition to that, if there's any kind of areas like bony prominences or areas that have fluctuating edema, often therapists localise some heat and then push that area out to put a little cavity on there as well. So loads of really subtle little design features that are often incorporated into these. And therapists do what they can with the resources that they have, but very much restricted by budgets that they have available. So if they try and make something fun and quirky, like using coloured thermoplastics or Velcro to help encourage participants or patients to actually wear their splints, but that, as I say, is very much down to whether they have it available in stock, down to budgets and such like. So patients might conceal their splints if they feel embarrassed by them, for example, or they might customise them, might end up drawing on them if they get bored, wrapping them up in all sorts of different things to conceal them. Because for many individuals, whether they feel embarrassed about wearing them in social situations, at work, for example, and particularly if it's a poorly fitted splint, it typically leads to poor compliance. So they're not going to get the full treatment benefits that would otherwise be anticipated from this. So the anticipated outcome of all of this, back when we started the PhD, was to essentially turn something like this into something a little bit more like jewellery. So this was Richard Bibb's vision back in the day, back in 2009, basically enabling better ventilation, something that the patient could customise in terms of aesthetics, form and function. And since the PhD started, there's been a flurry of other bits of research and commercial outputs from that. But certainly when I started, the only examples that we had to look at were by Fraunhofer. That was the first example that we saw of additive manufactured wrist splints and some work from Larry Ottman. But 2013 hit and there was a Cortex splint developed by Jay Kevel, and it absolutely spammed social media. Everyone was fascinated by it. And so if you search Google now for 3D printed splints, you'll find tons of stuff on there. There's a lot of commercial companies now offering 3D printed splinting, but typically a lot of these companies, particularly private sectors, require dedicated designers, engineers and such like to actually generate the geometry suitable for 3D printing additive manufacturing. So we were interested in part of the overall workflow, so we acknowledge that the actual scan data acquisition side is quite complicated. Thankfully, there's companies like Manometric who have developed a custom hand wrist scanning process, which looks to be very, very beneficial to overcome some of the limitations, but I'm not going to spend much time looking at the scanning side of this. I'm more interested in what do you do with that scan data next, and who is going to be using that data? How are you actually going to capture and manipulate that patient data? And there's tons of generics of engineering focused software available on the market. A lot of parametric stuff, but a lot of software which requires a lot of underlying sophisticated sort of training skill sets and such like to actually use it effectively. Takes a lot of time to use it effectively, very costly, and certainly the interfaces for lots of them are very, very complex, particularly if you don't really know what you're doing. So this is the interface for Autodesk Maya. A slight extreme example here, but there's just copious amounts of menus that if you were to ask somebody like a hand therapist who has no prior training or expertise in CAD, it would probably baffle them and they'd probably just be like, oh, no, I'll just go back to my thermoplastics, thanks. So we were really interested in understanding the tacit behaviours, what they do in clinics, and seeing whether we could replicate that in a virtual environment. So different things that we wanted to try out within our testing was whether we could have templates and such like. A lot of these examples are quite clunky, you know, things like having shrink wrap effects, whether we could physically replicate the draping effect onto a patient's scan as well, so they could see the literal links between traditional processes and a digital workflow as well. But we also found, after working with some hand therapists very closely, they actually really appreciated the ability to directly draw onto scan data, and they picked this up very, very quickly just by placing a series of landmarks directly onto it, and they found it much easier. And they often talked about when you're placing a patient's hand on a piece of paper, you're having to transfer 2D data to 3D, and a lot of mistakes are made through that process. So they actually found this quite useful. So we thought, okay, well, we'll work with this in a little bit more detail. So some of the other design features that we found, we worked on this, demonstrated that all of this is feasible. We can fill proximal edges, we can incorporate cavities over bony prominences, we can roll edges and things, and we can incorporate lattice structures to suit the patient and their requirements. So all of that was relatively straightforward. And then we were also interested in the ability to incorporate multi-material printing as well, so through the use of Connex back in the day and still continuing and such like. So the green area here represents a hinge, so the idea would be that you could have like a clamshell type design that literally opens up, enables an easier entry, donning and doffing for your patient. And the red area being a nice cushioned effect that could swell, accommodate swelling and change form as any kind of swelling occurs. So we made a custom software workflow in theory with all these different features in it, and then we translated it into basically a number of prototypes. So thank you very much, Dominic, for printing a load of splints for us. That was much appreciated back in the day. But really interested in not only incorporating custom lattice structures, but really discrete fasteners as well. So some of the examples we had, the idea was that if you've got someone with limited dexterity, they could pinch one half of it and the top would just pop off, and it would make it a lot easier rather than wrestling with Velcro and such like. And like I say, we were interested in multi-material prints to see what we could do with this, and then through consultation with hand therapists, they were really excited about this, such that they started proposing flexible materials, elastomer materials around the boundaries as well, so there's no need to flare edges or roll them, or rolling is a good idea anyway. But the key message here is that therapists are incredibly dynamic and come up with really interesting creative solutions to so many things. And they've been able to adopt and understand and explore new ideas for additive manufacturing and custom fitting devices. Another area we were interested in was laser sintered textiles as well. So we made some examples with these alongside our colleague Guy Bingham, and printed that, and it just falls really nicely, easy to get on and off, wouldn't hopefully cause any pain to an individual. And thank you very much to Candy at Sheffield for printing these as well, but really, really lovely things to hold on to and actually put on and take off. So it's all very well and good saying, oh, we've got these lovely prints, but actually we want to enable therapists to actually design and make these things. So back in 2011, 2012, I made a sort of visual prototype to represent what a custom software would look like or could look like, so that we could evaluate this with therapists. And it had all sorts of different controls in here relating to different material thicknesses and various other controls that they would typically need to have, like perforation density and various other bits and pieces. So we evaluated this with a number of therapists in the NHS that were primarily interested in the National Health Service. So it's a small scale feasibility study. We asked therapists to basically have a bit of a play with the software, see how far they got through it, and essentially had follow-up interviews to get their thoughts, their opinions on additive manufactured splints, but also the software that we were proposing. The main weakness of this, though, was the fact that this visual tool was only a tool, but we got overwhelmingly supportive feedback. The therapists were really interested in what we could offer, but it was just a visual tool. It wasn't a real CAD program. It was just a series of pictures to simulate it. So I thought, oh, you know, it served its purpose, but we subsequently got some follow-on funding from Arthritis Research UK to basically carry this through to make a fully functional bit of software. And so we started using a program called Grasshopper, built within Rhino, to basically enable all of these design features so that therapists could create custom boundaries for their splints. There's a certain amount of automation here where it's necessary, where, say, for example, putting in fasteners, they don't necessarily or wouldn't necessarily need to spend that time invested in positioning fasteners, but we could, say, automate them, but give certain controls. But but all the areas where the therapists would need to have their clinical rationale and justification for positioning certain things, they would still maintain that ability to do that. Linking on from what Yari was saying earlier, having certain abilities to enable them to capture their design intent, but automating some of the stuff that that isn't necessarily needed by them. So again, we evaluated this with a number of hand therapists throughout the UK. Again, overwhelmingly supportive. Every therapist was able to use this within, say, 10 minutes, had a viable 3D scan model suitable for 3D printing. And we've subsequently released this just as a proof of concept prototype that people can basically have a look at, watch the video. We've got a dedicated website for this now, if anybody's interested. It is still under development, admittedly. We certainly aren't recommending that this actually be used in clinics, but if it does give any kind of useful insights or guidance for those that are interested in developing a regulated software in a commercial sense or whatever it is, then it's very much, you know, talk to us. We're very interested to hear from you. Some other work that we've been doing as well, just quickly, some other prototypes that Joe's been working on, some lovely examples there. So please do pop by and have a look at the website. So it would be wrong for me to say this is the only example of software out there. There are splinting software programs now commercially available, but they can be expensive. They claim to automate the design process. Say, for example, lots of them claim that, you know, you just have a planar chop across the fingers, but that limits the motion, the flexion at the fingers. So lots of those tacit decisions of therapists are often missed. So just to sort of finish off, because I can see Kenny getting twitchy, don't worry. To what extent is automation the best solution? And I always think that it's really important that we take into consideration therapists and their requirements as we're developing these software tools, making sure that patients get the best fit, comfort, and to enable them rather than making their professions obsolete. And I'll summarise that. But yeah, thank you very much for listening, everybody. Hope that was interesting for you all.
Yeah, that's great. Thank you.